this video, we want to find the points or point on the ellipse 9x squared plus y squared equals 9 that is closest to the point 0, negative 1. So we are trying to find points that are closest to one another, so we're going to be trying to find a minimum. But before we even get there, I think it's going to be most useful to take a look at the graph of this ellipse. So I'd recommend that you either get out your graphing calculator or open up Desmos, and let's take a look at what the graph looks like. So I'm going to use Desmos, and I am graphing 9x squared plus y squared equals 9. Looks like I missed a square there. All right, there we are. So here's our ellipse. It looks like a stretched out circle, if you will. And you can see this particular ellipse is long vertically. It has a vertical major axis. And I'm going to change the settings on Desmos here. I'm going to go ahead and just use a step of 1 for both x and y. And then I like to turn off my minor grid lines just to have a clearer picture. So there's the ellipse that we are working with. And this problem says that we want to find the point on the ellipse that is closest to this point here, which is 0, negative 1. So if you just kind of eyeball where you would be located on the ellipse and be as close as possible to this point, 0, negative 1, and you might say you'd be somewhere about here. Maybe that point, somewhere in that region, would be as close as possible to the point 0, negative 1. So this unknown point, the point that we don't know, since it is unknown, we're going to go ahead and give it a variable name. We're just going to call this coordinate x, y. And we are interested in finding the smallest distance between these 2 points. I'm going to call the distance between my points d. So therefore, I am interested in actually minimizing the distance between these 2 points, the distance between the point xy and the point 0, negative 1. So now that we have a visual, let's go ahead and, if I can, successfully move that graph out of the way for now. Let's write down our goal. So the goal is to minimize distance. And we specifically want to minimize the distance between the 2 points, the unknown point, which is x, y, and the point that we were given, which was 0, negative 1. We want to minimize the distance between these 2 points. So to compute the distance between any 2 points on the coordinate plane, we can utilize the distance formula, which is going to be the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. That'll compute the distance between any 2 points on the coordinate plane. So the distance between our points will be the square root of x minus 0 squared plus the quantity y minus negative 1 squared. And if we simplify, this will be the square root of x squared plus y plus 1 squared. So this is a great equation that relates x and y and d being distance. However, if we are ultimately trying to compute a minimum, then we have too many variables here. We have 2 inputs and 1 output, which is no good. We need to have just 1 input and 1 output. So I have to kind of pause right now on this equation that we've written because we have too many variables. We kind of need to go back and look at our picture and see if we can come up with another equation that relates our variables. So I'm going to scoot over here and see if I can pull my graph back successfully. Okay, sorry, it took me long enough. So we need to look at the coordinate that we were given, which was the coordinate xy. And you'll notice something about this point xy. This isn't just some random point. It's not like a random point in space over here, but rather the point xy, it has to be a point that is on the ellipse. See, if the point was way up here in the first quadrant, then the distance between the ellipse and the coordinate 0, negative 1 would be much larger. And we're trying to figure out what point would we be at on the ellipse so that the distance is as small as possible? But that coordinate xy, again, it has to live, if you will, it has to live on the ellipse. It's not some random point in space. So since it lives on the ellipse, then that tells us that the equation or the relationship between x and y, it must be the ellipse equation, 9x squared plus y squared equals 9. This ellipse equation will give us every possible coordinate that is on this ellipse that creates the actual curve of the ellipse. So the constraint equation, that the limitation in this case, is actually the equation for the ellipse that we were given. So let's go back to our work, and we should be able to write our constraint equation. All right, so the constraint equation, which was given to us, and I actually like to label it as the constraint. So my constraint is the equation for the ellipse, which is 9x squared plus y squared is equal to 9. Now, the purpose of this equation is to solve for either x or y, so we can substitute into our distance formula. However, in this case, you'll notice there's an x squared already alone, so it might be beneficial actually to solve for x squared here rather than solving all the way for x, because we could just go ahead and substitute, and that may save us a little bit of work. So again, it is okay if you chose to solve for y. No problem. You can solve for y if you want. I'm just choosing to solve for x squared, seeing that it might save me a step or two. So 9x squared equals 9 minus y squared. And then I'm going to choose to divide by 9, and I like to divide each term. So therefore I can simplify both of those terms. X squared equals 1 minus y squared over 9, which I'm going to rewrite as 1/9 y squared. And then rather than square rooting both sides, I'm going to leave my equation like this, and I'm going to go ahead and substitute this expression for x squared into my distance equation here. So x squared is 1 minus 1/9 y squared plus the quantity y plus 1 squared. Now, we're ultimately trying to compute a minimum. So we're wanting to use the derivative because the first derivative will help us find maximums and minimums. And I can leave it like it currently is, or I could do a little bit of algebra first, and maybe that would make the calculus a little simpler later on. So I'm going to choose that. It's either algebra now or algebra later. I'm choosing algebra now. So we want to go ahead and multiply out the y plus 1 squared, which will be y squared plus 2y plus 1. And then we notice we've got some like terms here. We have negative 1/9 y squared and a positive y squared. And we also have 1 plus 1. So we can simplify a bit more. So the distance is going to be negative 1/9 y squared plus a 1y squared will give us a total of 8/9 y squared plus 2y plus 2. So here is our distance function, the distance function. And it is in terms of y. So now we're ready to go ahead and compute our derivative. So now notice this square root is really a function raised to the 1/2 power. So this is essentially going to be a composite function, so we need to apply the chain rule. So the derivative of a quantity raised to the 1/2 power will be 1/2 times the quantity raised to the negative 1/2 power. And then we have the original inner function, which is 8/9 y squared plus 2y plus 2. And then remember, the chain rule requires that we take the derivative of the inner function and we chain that derivative on with multiplication. And the derivative of 8/9 y squared, the 2 will come in front and be multiplied by the 8/9, so that would be 16/9 y plus the derivative of 2y, which will just be 2. And then it's worth noting that we have a negative exponent, and whenever we have those negative exponents, it's usually easiest to go ahead and rewrite this expression so it doesn't have a negative exponent, so we can put that in the denominator. So this is going to be a somewhat messy looking fraction. We'll have 16/9 y plus 2 in the numerator. And then in the denominator, we still have a 2 from the 1/2. And then we'll have the 8/9 y squared plus 2y plus 2. And that will all be raised to the positive 1/2 power. So that's a biggie. There is our derivative. Now, from here, we want to find our critical numbers. So we're going to branch off and we're going to solve for where the derivative is equal to 0. And then we'll also consider where the derivative may be undefined, because we're looking to find a change in the sign of the derivative. Remember, if we're searching ultimately for a minimum, then if we have a minimum on a graph, then the slope of the tangent goes from negative to positive. So we're looking for this change in sign on the derivative. And that's why we're looking for these critical numbers, because those are the potential places where the derivative might change sign. So to set this big derivative equal to 0, since it is a massive fraction, we really only need the numerator to equal 0. If the numerator of a fraction equals 0, then the entire fraction will be equal to 0. So we'll solve 16/9 y plus 2 is equal to 0. So we'll subtract 2, and then we'll multiply by the reciprocal. So negative 2 times 9/16. So it looks like y is equal to negative 18/16, which we can simplify to be negative 9/8. Negative 9/8 looks to be a critical number. But then we also have to consider where the derivative may be undefined. And since this is a fraction, we realize that a fraction would be undefined if you have 0 in the denominator. And the only way for that to happen is if the 8/9 y squared plus 2y plus 2 were to be equal to 0. So we're going to just include what's inside the radical. Remember, that's called the radicand. And we're going to go ahead and set that quantity equal to 0. And this gives us a little deja vu maybe from our college algebra days, where we are solving a quadratic equation. And we're probably not too happy about it because we don't like that fraction. We're interested in trying to factor this. And so you could try to factor it in its current form, or you may be a person that doesn't like the fraction, the 8/9. So you might choose to multiply both sides of this equation by 9. And in doing that, I'm multiplying by 9 because that was the denominator, and that's going to let us eliminate the fraction. So we would end up with 8y squared plus 18y plus 18 equals 0. So now you could try to factor it, or you may just bail on that method and go ahead and try to use quadratic formula. Or, of course, you could technically go to your calculator and, of course, solve the quadratic equation graphically on your calculator. I'm going to go ahead and show quadratic formula. So we have y is equal to negative b, or the opposite of b, which would be negative 18, plus or minus the square root of b squared minus 4ac. So that's 18 squared minus 4 times 8 times 18, all divided by 2 times a, 2 times 8, which is going to be 16. And at this point, you could certainly grab your calculator and compute this, or you might just look at this radical and notice 4 times 8 is 32. So we end up with 32 times 18. But 18 squared is 18 times 18. So no matter what, 18 times 18 minus 32 times 18, that's going to give me a negative number inside this radical. If you had gone to your calculator, you would be getting an error, and perhaps you might be frustrated, but you got to realize, wait a minute, I'm not getting any answers here, and that's because I end up with non-real answers. These turn into imaginary numbers. These are non-real. So that means that we don't have a time where the derivative is undefined. We don't get any additional critical numbers. So the only critical number is negative 9/8. At this point, you might be jumping for joy like you're done. Finally, it's the longest problem perhaps of your life. But don't get too excited, because I'm always going to tell you to go back to the original problem and let's be sure that we answer the question. So in this case, it doesn't just ask you to find the y value, but it says to find the point or points on the ellipse. And that means we need not just the y value, but also the corresponding x value. So we need to take our y value that we found. And you know what? Actually, I'm jumping the gun. Pause for a moment. I'm so sorry. Before we want to search for our corresponding x value, we better pause for a minute and actually double check and verify that this actually yields a minimum. That would be a poor choice to move on before we know for a fact that we have a minimum. I got excited. I thought we were almost done, and we are. We're close. But time out. We need to pause and do the first derivative test here and verify that we do have a change in sign. We need this derivative to change from negative to positive in order to verify that we have a minimum. And this verification step is really important, especially it's a good way of checking your work. So we're going to test some value smaller than negative 9 over 8. How about negative 2? And a number larger than negative 9 over 8. I'm always one to test for 0 if I can. And remember where you're testing, we're testing all the way back into the derivative because we're looking for the sign of the derivative. So go ahead, this is where you could pause your video, grab your calculator, you could go ahead and substitute, or by hand you could substitute in negative 2 into that derivative, and let's see what the sign is of the result. So hopefully you paused, and when you substituted in negative 2, you should be getting a negative result. And when you substitute in 0, you should be getting a positive result. Thank goodness. So that does verify what we had hoped, that the derivative changes from negative to positive, which means we have found with confidence that we have a minimum at y equals negative 9/8. So now we want to find the corresponding x value, and the original equation for the ellipse was 9x squared plus y squared equals 9. And if you take a look at your constraint, notice we actually already solved for x squared. We had x squared equals 1 minus 1/9 y squared, if you look at your constraint work. So you might as well use that constraint since it was close to solving for x. And let's just go ahead and substitute in the y value that we just computed. So our y value was negative 9 over 8. And we will solve for the corresponding x values. So x squared is equal to 1 minus 1/9 times 81 over 64. Notice that the 9 divides into 81 9 times. So we end up with x squared is equal to 1 minus 9 over 64. And you might beat me using your calculator, but I'm going to go ahead and try to finish this to the end by hand. So this would be 64 over 64 minus 9 over 64. Getting a common denominator leaves me with x squared is equal to 55 over 64. And then we will square root both sides, and we end up with x is equal to plus or minus the square root of 55 divided by the square root of 64, which I'm going to simplify to be 8. So that tells me, this is interesting, we ended up with two different x values. The square root of 55 over 8, that corresponded with the y value of negative 9/8, but we also had the negative square root of 55 over 8, which corresponded with negative 9/8 as well. So right now it looks like there are actually 2 points on the ellipse that will be a minimum distance from the point 0, negative 1. And before we're done, I want to go back to our graph briefly just to verify why would we get two possible different x values, and why would our y value be negative. notice our y value, which was negative 9/8, that makes sense because if you look at the location on the ellipse, the point that's closest to 0, -1 is going to have a y value that is below the x-axis, so the y value would be negative. And then the reason why I would logically get two possible x values is because I would see that there is another point on the ellipse that's in the third quadrant that would also be the same distance away from 0, -1. So there's another point here and it would have a negative x value. Because of the symmetry here of this ellipse, it's symmetrical with respect to the y-axis. So this is why we're getting two different x values, one positive, one negative, yet we're only getting one y value, which is negative.